Okay, so we have seen that for the long line case. So this is the relationship that sending end voltage and receiving end voltage and receiving end current, and this is for the sending end current, that relationship that receiving and this is receiving voltage and this is receiving end current, and these are all cos and sine hyperbolic terms, right. Now, that very one thing is very understandable to you, that this is ABCD parameter. So, A actually is cos hyperbolic gamma L, and this is your B is ZC sin hyperbolic gamma L, right, and your C is 1 upon ZC sin hyperbolic gamma L, and A is equal to D. So, here also D is equal to cos hyperbolic gamma L, right. This is the exact one. Now, what we want actually, we want to represent this that your exact your calculation of ABCD parameter, that uniformly distributed parameters, right, in your pi representation. So, what will be the equivalent pi representation? Now, I will show you how to do it, right. So, in this case, so this is the pi model. How it is coming, I will tell you. So, this is your equivalent pi model. So, it is z dash is equal to z sin hyperbolic gamma L upon gamma L, this is z dash. What is z dash? I will come to that. Then y dash upon 2, and I mean it instead of z, this has become your z dash. Generally when we are doing in a pi model, right, when you are doing in a pi model, at that time it was z and y by 2, but as you have taken the exact one, there, so this z actually will be multiplying by a factor sin hyperbolic gamma L upon gamma L. It is coming from that only, I will come to that. And instead of y by 2, this side is y dash by 2, this side is y dash by 2, and y dash by 2 is equal to y by 2. When we did ABCD parameter for pi model, it was only y by 2, but y by 2 is multiplied with tan hyperbolic gamma L by 2 divided by gamma L by 2. So, how this is the how things are coming, I will come to that, but this is that your what you call that pi representation of long line, right. Now, if you see that for pi network, that sending end and receiving end your relationship, this is your what you call, this is Vs, that is A is equal to, this is for equation 15 and 17, that you go back to that thing, that pi method, pi model for ABCD parameters. This is 1 plus z y upon 2, this is z, this is y into 1 plus z y up by 4, and this is 1 plus z y by 2, A is equal to D, no. So, same this equation. So, when we are representing long line in pi representation, what we are doing is, we are instead of writing z or y, we are replacing them by 1 plus z dash y dash by 2 Vr, right, plus z dash Ir, and Is is equal to y dash 1 plus z dash y dash upon 4 into Vr plus 1 plus z dash y dash by 2 into Ir. This is equation 44 and this is equation 45, right. So, what you have to do is that you have to, that means this long line expression, that means this expression, this is the exact expression, right. This, but we want, instead of taking your what you call ABCD of this, we want to replace this one by an equivalent pi model, right. So, in that case what will happen, that we will get this one. How we will get it? Now, I will show you. So, what you have to do is that we have taken that 1 plus z dash y dash upon 2. So, z dash and y dash we have to obtain. So, in that case what we can do is, you compare equation 44 and 45 with equation 40 and 41 and making use of this identity, right. So, what you have to do is that in that case, in this case, look, that first you use this mathematical identity, that tan hyperbolic gamma L by 2 is equal to cosine hyperbolic gamma L minus 1 divided by sine hyperbolic gamma L. This relationship we will use, this equation number I have made 46, but this equation we will use. Now, what we will do is that this is z dash Ir, right. So, we have taken that means this is your this is your what you call, this is A B C D parameter, right, A B C D parameter, and you know that B is equal to your Z, right. From this equation, you that equation 18 for normal pi, you know B is equal to Z, right. But here we are taking that B, here it is instead of Z we are writing this one your what you call Z dash, this is Z dash. So, Z dash actually your basically this is your Z dash is equal to ZC sin hyperbolic gamma L, right. Therefore, this Z dash is equal to, you are writing your sin ZC sin hyperbolic gamma L, right, is equal to I will give you the next page, I will give you that how it is coming, is equal to, you can write Z into sin hyperbolic gamma L divided by gamma L, this is equation 47, and y dash 2 is equal to y by 2 into tan hyperbolic gamma L by 2 by gamma L by 2. This 2 how it is coming, I am coming to the next page, right. That using this, I mean when you get this thing, so you can represent that long line by an equivalent pi representation, right, for long transmission line. This is IS, this is IR, this sending end current, receiving end current, right. This is VS, this is VR, and this is y dash by 2, and this is also y dash by 2, and this is your Z dash is equal to Z into sin hyperbolic gamma L upon gamma L, and this the original I mean I mean when you consider only pi model, at that time this hyperbolic term was not attached, right. So, that means Z is multiplied by this factor, and similarly y by 2 is multiplied by this factor. Earlier it was only Z and y by 2, but as long line the more exact one, this here and here these two factors are multiplied. Similarly, here also not showing is, here also y dash by 2 means the same thing, right. So, now how these two things are coming, this Z dash is equal to this one and y dash by 2 is this one, right. Look, I am coming to that. Next, that this one actually Z dash is equal to your ZC, look at this side, right, this side, Z dash is equal to ZC sin hyperbolic gamma L. So, we know your ZC is equal to, you know, root over small z by small y, earlier we have defined, right. So, numerator and denominator, this here you multiply by your this thing z, and here also z. So, z square, so z will come out from the root square, and this thing it will be root over yz, right. But we know propagation constant gamma is equal to root over yz, that also we have seen earlier. That means zc will be small z by gamma, right. Now, numerator and denominator you multiply by L, that length of the line. That means it is because z is your impedance that ohmic values, that line impedance per unit length. So, ZL upon gamma L. So, that means capital Z is equal to small z into L. Earlier we have seen that this is the total impedance, and this is ZC is equal to Z by your gamma L, right. Therefore, if ZC is equal to Z by gamma L, then that your that parameter in that equation you can submit, you can put this one, right, that your Z dash is equal to ZC sin hyperbolic gamma L. So, ZC is equal to Z by gamma L, right. So, here you substitute that ZC is equal to Z by gamma L. So, it will be Z into sin hyperbolic gamma L by gamma L, here you have put it, right. That is why Z dash will become Z into sin hyperbolic gamma L upon gamma L, this is the Z dash. Similarly, from that relationship we know 1 plus Z dash y dash by 2 is equal to cos hyperbolic gamma L, right. So, if you look into this this expression, your ABCD parameters, A is equal to 1 plus Z dash y dash by 2, because you want to represent that equivalent pi, and A is equal to cosine hyperbolic your here A is equal to cosine hyperbolic gamma L, right. Therefore, 1 plus Z dash y dash by 2, that is your A actually, or A dash rather, right, is equal to cosine hyperbolic gamma L, right. Therefore, Z dash y dash by 2 is equal to cos hyperbolic gamma L minus 1, right. Now, that means y dash by 2 is equal to cos hyperbolic gamma L minus 1 divided by Z dash, right. Therefore, this Z dash is equal to your Z into sin hyperbolic gamma L upon gamma L. So, what you can do is that this here first, that cos hyperbolic gamma L minus 1 divided by sin hyperbolic gamma L, actually it is equal to tan hyperbolic gamma L by 2. So, that means this y dash by 2 can be written as 1 upon ZC into tan hyperbolic gamma L by 2, right. So, we have seen, we know that Z c is equal to here root over Z y. So, here numerator you multiply by numerator and denominator multiply by y. So, it will be root over Z y upon y, and gamma is equal to root over Z y. This is actually small z, this is actually small z, right. So, this is gamma by small y. Now, numerator and denominator you multiply by L. So, gamma L by small y into L. So, Z c will be gamma L upon capital Y, right. Therefore, 1 upon Z c is equal to y upon gamma L, right. So, here 1 upon this 1 upon Z c here you put here that 1 here, right. So, 1 upon Z c is equal to you put y upon gamma L, then you will get y dash by 2 is equal to y tan hyperbolic gamma L by 2 divided by gamma L, right. That means, this one to make the this y dash by 2, here also you make y by 2, but this one you write tan hyperbolic gamma L by 2 by gamma L by 2, because 2 will be cancelled actually, but to make it y by 2 into tan hyperbolic gamma L by 2 gamma L by 2. That means, this y by 2 is multiplied by this factor for a long line by your pi representation, right. That is why this your what you call this diagram pi equivalent, it is your this kind of pi representation. So, z multiplied by this term and y by 2 multiplied by this term, but let me tell you that this term and this term are, you will find approximately this sin hyperbolic gamma L by gamma L approximately your very close to unity, right. Here also the same thing, this term, right, but this is that more or less quite accurate model, right. So, up to this we have come for short line, medium line and long line, right. So, now we will see few examples, after that we will go to some more details of this characteristic of the transmission line, right. So, first you consider that example 1, first example will be a single phase line, but let me tell you one thing, whenever you will solve numericals, even it is 3 phase, you transform all the parameters first per phase basis, right, line to neutral, after that you solve it. So, first you see this, a single phase frequency 60 Hz generator supplies an inductive load of 4500 kilowatt at a power it is power factor, right, it is at a your power factor, I have missed this, power factor of 0.8 lagging, right, by means of an 20 kilometer long overhead transmission line. The line resistance and inductance are 0.195 ohm and 0.60 millihenry per kilometer. The voltage at the receiving end is required to be kept constant at 10.2 kV. That means, receiving end voltage is kept constant at 10.2 kV. You have to find out the first one, find A, the sending end voltage and voltage regulation of the line. Now, part B, the value of the capacitors to be placed in parallel with the load such that the regulation is reduced to 60% of that obtained in part A, and C, compare the transmission line efficiencies in part A and part B. So, these are the things you have to find out, right. So, you have to find out that your what you call that your sending end voltage and voltage regulation, at the same time that the value of the capacitor to be placed your in that receiving end, that is across the load in parallel, right, such that whatever regulation you got in the first case, it should be 60% of that. That means, you have to improve the power factor and you have to find out what is the value of C, and that is the problem, but this is a single phase line, this problem is a single phase line, right. Now, how to do this? Look at this side only. The line constants are given, R is equal to 0.0195, the 20 kilometer length, because it is ohm per kilometer. So, it is 20 kilometer length multiplied by 20. So, 0.39 ohm, right, and x is equal to your given millihenry per kilometer. So, that is your L is given that millihenry per kilometer. So, 0.6 into 10⁻³ into 2 pi 60 Hz system into 20 kilometer the length of the line. So, it is 4.52 ohm. Now, come to the part A. This is short line, right. So, for short line, no question of considering charging admittance. So, I is equal to IR is equal to IS, because short line has no shunt capacitance there, that is the charging capacitance, I mean that is that charging capacitance. So, I is equal to I r is equal to I s, right. So, first you find out that magnitude of the current, it is load is given at kilowatt and this is kilovolt of course. So, 4500 divided by 10.2 and power factor is 0.8, that is V I cos phi, actually V I cos phi is equal to power. So, mod I is equal to a writing like this is ampere. So, magnitude of the current is 551.47 ampere. First you compute the current. Now, from equation 6 we have seen no magnitude of V s is equal to magnitude of V r plus magnitude of I into r cosine delta r plus x sine delta r. So, receiving end voltage is kept fixed at 10.2 kilovolt kV. So, is equal to write 10,200 volt, all unit we are transferring into volt here, and power factor is given. So, cosine delta r is equal to 0.8. So, sine delta r is equal to 0.6, right, and r and x values are known here. So, substitute everything here, and I is also known, magnitude of the current 551.47, you substitute all, right, and put it here. So, you will get sending end voltage is equal to 11.867 kilovolt, right. So, voltage regulation formula we know for your what you call for short line, right, it is magnitude V s minus magnitude V r upon magnitude V r into 100. So, substitute here V s is equal to how much, V r is equal to how much, and here also the regulation will become 16.34%, right. So, this is that voltage regulation with respect to that, basically we compute with respect to the receiving end voltage, right. Now, in the part B is showing that you have to improve that voltage regulation, that means in that first part regulation was 16.3, but in the second part we want to make it is 60% of this voltage regulation by connecting a shunt capacitor across the load. So, this is a short line. So, this is resistance R, this is X and current flowing to this is I r, this one capacitor is connected across the load. So, this is the I c, that is current going to the your capacitor, and this is the current I going to the load, right. So, it is a simple series parallel circuit, right. You have whatever you have done in your basic circuit problem also to improve the power factor, you might have taken many your what you call such kind of circuit problem, but here it is power system problem, right. So, therefore, under this condition regulation we want that it should be, but receiving end voltage is kept fixed at 10.2 kV, it is unchanged. Therefore, if regulation is known, this is 9.804%, you know the regulation formula. So, mod V s minus mod V r upon mod V r. So, magnitude V r is 10.2. So, 10.2 is equal to this, that means sending end voltage is 11.2 kV, right. So, with this regulation if you want to keep this receiving end voltage fixed at 10.2 kV, then sending end voltage magnitude will be 11.2 kV, right. So, this is that equivalent circuit diagram when you have connected a capacitor. Now, again using equation 6, right, using equation 6 we can write magnitude of V s is equal to magnitude V r plus magnitude I r, because this is the current, please do not take this current, you have to take the receiving end current, right, this take this current, one part is going to capacitor, another part going to I, but when you will write this equation please do not take this I, then there will be mistake, because you have to take receiving end current, because voltage is parallel. So, voltage across the load or across the capacitor is same, right, and this load is known, and if load is known, that equivalent your what you call equivalent load or equivalent impedance can be obtained. So, do not take I, you have to take this I r, this is I r, right. So, be careful about that. Sometimes a common silly mistake means, oh, current is going to load, that means this is I r, no, this is incorrect if capacitor is connected, right. So, this is your I r, right. So, magnitude V s is equal to magnitude V r plus I r, then we are as the capacitor is connected. So, delta r will change. So, r cosine delta r dash we are taking plus x sine delta r dash, right. So, magnitude V s minus V r is equal to I r magnitude of course into that r cosine delta r dash plus x sine delta r dash, right. Now, actually capacitor we assume this is I mean capacitor has no your what you call not consuming any real power, but little bit is there, but we will neglect that, right. So, we will assume the capacitor consume only reactive power, right, but no real power. So, since the capacitor does not draw any real power, right, as it is not drawing, we have magnitude of I r we are writing is equal to, this is the load power 4500 kilowatt and receiving end voltage is kept fixed at 10.2. This is cosine delta R dash. I am putting the unit here ampere, because this is numerator, this is in kilowatt, I did not change it to watt, and denominator also 10 kilovolt. So, no need to change it again, right. This no need to multiply by 1000, or this is 1000, understandable, into cosine delta R dash. So, this is that your what will be this, that IR, because capacitor does not any your what you call that your any real component of that your what you call does power, right. Therefore, that combination of IR will be the same thing, 4500 10.2 cosine delta R dash ampere. So, from that you, but you have to find out your cosine your what you call, this is equation 2 I have marked, and this Vs minus Vr I have marked equation 1, right. This is 1 and this is 2. So, I hope you have understood this, right, a very simple thing. Next is that Vs is given 11.2 kV and Vr also given 10.2 kV, this all these things are known to you, right. So, you have to substitute, what you will do is that you from equation 1 and 2, as these two are known, IR is also known, R and X value is also known, you have to find out delta R dash, right. So, from equation 1 and 2, so you will substitute here, it is Vs is equal to 11.2 and Vr is equal to 10.2, you will substitute here, IR also this one you will substitute here, and R values and X values also known, R and X you substitute here, and you will simplify a little bit, right. I did not write all these steps, but these are simple thing, you will substitute. If you do so, then you will get, that is why I am writing from equation 1 and 2, from equation 1 and 2, right. After substituting a little bit simplification you do. So, what you will get? You will get 4.52, then tan delta R dash is equal to 1.876, right. That means, tan delta R dash is equal to 0.415, hence delta R dash is equal to actually 22.5 degree, right. So, cosine delta R dash is equal to 0.9238, this is the your improved power factor, right. Earlier it was 0.8, now it is 0.9238, because you want to maintain the regulation to 60% of that without any your capacitor across the load, right. And as cos delta R dash is 0.923, now from here you substitute now cos delta R dash 0.9238. So, if you do so, then magnitude of IR, that current magnitude, you will get 477.56 ampere, this is the current. Now, from this circuit, IR is equal to IC plus I, right. So, IR is equal to I plus IC, right. So, IC is equal to IR minus I. So, IR your what you have to do is that you have to, now IR is 477.56, this is the magnitude of the current, and this delta R dash is 22.5 lagging. So, IR is equal to 477.56 minus 22.5 degree, this is your IR, right. And I, that is the current going to the load, we have obtained no 551.47, right. This is that current going to the load 551.47, and power factor is your 0.8, it is lagging. That means, your I is equal to, I mean this one, right. I mean this one, this I, it is going to the, it was for first case it was going to this load, no, this current, at that time it was IR, because at that time shunt capacitor was not there in the first case, right. So, I is equal to 551.47 angle minus 36.86 degree, 87 degree, right, and this is your IR, that is after putting that shunt capacitor. So, now that means your IC will be your IR minus I. So, IR minus I, right, and you will get IC is equal to J 148.13 ampere, right. So, now this is your current is leading, that is capacitor. So, J is there, current is leading, right. So, you can take more decimal places, I will explain little bit later. So, Xc is equal to 1 upon omega c is equal to Vr upon Ic, the magnitude, right. So, Vr is 10.2 into 1000, we have made it to volt, because current here is in ampere. So, divided by 148.13. So, that means omega is equal to 2 pi, we have taken 60 Hertz system. So, 2 pi 60 into C is equal to 10,200 by 148.13. Therefore, if you calculate C from here, C will become 38.5 microfarad. This is the capacitor, right, capacitor value. So, what we have observed that it was your earlier it was minus 36.87 without capacitor. Now, when you put the capacitor, it is minus 22.5 degree, that current your lagging. Earlier it was minus 36.8, but we have got the capacitor C 38.5, but how much reactive power actually supplied by the your capacitor, right. So, that also you have to get it. So, in this case, first thing is when there was no capacitor, that reactive power absorbed by the load is QL is equal to your, I can put like this, QL is equal to PL tan phi, right. So, that means when you write the power, P I am putting in L, J QL, that is load power, right. This is that your S we write, that means your tan phi is equal to QL upon PL, right. That means QL is equal to PL tan phi, right. That is why we are writing that reactive power absorbed by the load QL is equal to PL tan phi, a simple thing. So, PL is equal to 4500 kilowatt and your cos phi is 0.8, your cos phi is 0.8, then sin phi is equal to 0.6, sin phi is equal to 0.6, right. Therefore, tan phi is equal to 0.6 by 0.8 is equal to 0.75. That is why that is your 4500 into 0.75 kilowatt, that is QL is equal to 3375 kilowatt, right. This is that your what you call load reactive power. Now, when capacitor is connected across the load, that combined power factor we have got cos delta R dash is equal to 0.9238, right. This one we have got it. Cosine delta R dash is equal to 0.9238, this one we have got it, right. Therefore, tan delta R dash is equal to 0.415 I have taken, but I also add 3 more digit 044, you can go up to 3 digit only, right. So, if this is that cosine delta R dash is this much, therefore, tan delta R dash will become this much, right. Therefore, reactive power absorbed by the combined load and capacitor, right, that QL dash I have made it is equal to 4500, because load power is real power and capacitor is not drawing any real power, only reactive power. So, we can write 4500 into this tan delta R, here it was PL tan phi and here it is your what you call this thing, this phi actually there should not be any confusion, that phi actually you can take your delta R, right. Generally sometimes we write phi only, but phi is equal to delta R, right, same thing. So, in this case what you can do is that it is QL dash is equal to 4500, as capacitor does not draw any real power. So, real power will remain same into this tan of delta this thing your delta R dash. So, there should not be any confusion, right. So, tan phi actually is equal to tan delta R, right. Therefore, we can, if you want to put that your this thing what you call this QL dash is equal to this one kilovar multiplied by this tan value. So, QL dash is equal to 1867.7 kilovar, right. Therefore, reactive power this is the combined one, the reactive power supplied by the capacitor will be QC is equal to QL minus QL dash, because this was QL and combined one was this one 1867.7, then how much supplied by the capacitor, that QL minus QL dash, that is equal to 1507.3 kilovar. Now, QC is equal to IC square into XC. Now, we have to verify the result, right, that whether we are correct or not. Now, with QC is equal to IC square XC if you make, because current going through this capacitor is IC and XC is the reactance, therefore, that XC is equal to QC upon your what you call IC square, it is kilovar. So, 1507.3 10 to the power 3 and this is the 148.13 is that current, right. So, IC is that 148.13 magnitude. So, XC is equal to 68.7 ohm. Again XC is equal to you can write VR upon IC, this is VR upon IC, this is 68.8 0.8 ohm. The difference is here it is 0.7, 0.8, 0.1 ohm. Thank you. I am coming to next.